Okay, let's go over a couple of the ones on the 5/8 homework. Let's look at, let's say, number 3. All right. I'd want to get all my x squareds on the same side. That'd be a good place to start, right? So why don't we subtract 4x squared? That gives me negative 3x squared. We could also add the 7 and add the 7 over here, and that would give me 12 on that side. So now we have negative 3x squared equals 12. Divide both sides by negative 3. X squared equals negative 4. To undo something squared, we take the square root of both sides. When we take the square root of both sides, we're always going to have a positive and negative answer. Now let's look at the square root of negative 4. It's the square root of a negative number, so that would be I, and the square root of 4 is 2, so that would be rewritten as plus or minus 2i. On the next problem, we would maybe distribute the 2. 2x squared plus 14 equals x squared plus 10. Again, like we did here, try to get all your x squareds on the same side. And then also get all your constants on one side. So I get x squared equals, and then 10 minus 14, that'd be a negative 4. Very similar to this one. I know I would take the square root of both sides and get x equals plus or minus the square root of negative 4, which is going to be plus or minus 2i. Anytime you have a negative under the radical sign, you're just going to have an imaginary answer. All right, number 6 would be also a good one to look at. Subtract 17 from both sides, and I get x cubed equals 115. Take the cube root of both sides. Now when we take the cube root, we don't have that plus or minus option, so it's just positive since the original was positive. That breaks down to 5 and 23. There's no perfect cubes in there, so you're done. Now this problem, I believe, was rewritten. I believe we changed that one to x plus 3 squared equals 45. Now we have something squared equals a number, so we can take the square root of both sides. When I take the square root, I have two options. I'm going to have a positive or a negative answer. So now we look at 45. 45 is really 9 times 5. So I can break that down into the square root of 9, which is 3, times the square root of 5. Now I want to get x all by itself, so subtract 3. So we'll get 3 root 5 minus 3. Or you could write it as negative 3 plus or minus 3 root 5. There's two ways you could write that, and they'd be fine. Now, on number 8, I actually think I need a little bit more room, so I'm going to rewrite that one on another sheet of paper. We have f of x equals x plus 2, x squared minus 9, x squared plus 9, and x squared minus 5. And it says to find the roots. Now remember, the roots of a polynomial mean when does this whole thing equal 0. Well, remember, if the whole thing equals 0, then one of these factors has to be 0. So either x plus 2 equals 0, x squared minus 9 equals 0, x squared plus 9 equals 0, or x squared minus 5 equals 0. We have 4 separate equations to solve. That's it. X plus 2 equals 0. Subtract 2 from each side. We get x equals negative 2. X squared minus 9. add the 9. I get x squared equals 9. Take the square root of both sides. Remember, I always have a plus or minus. And the square root of 9 is 3. X squared plus 9. So it's very similar, but we have a plus here. So we're going to subtract 9. And I get x squared equals negative 9. I hope somebody is saying in the room, I'm fixing to take the square root of a negative number. I bet it's going to be imaginary. And it will be. Still x squared, so I have that option of a positive or a negative answer. The square root of negative 9, we know the square root of 9 is 3, and since it's negative, it's going to be 3i. The last one, add the 5. And I get x squared equals 5. Square root both sides. X equals plus or minus the square root of 5. And you're done. Now, in the last problem, you're supposed to kind of work backwards. And I want you to really compare this problem and the next one. The next one says, what if I'm instead given the roots? Could I work backwards and figure out the polynomial? So, the roots are 2, square root of 3, and 3i. If those are the roots, then that means there had to have been a factor that when I set it equal to 0 and solve for x, those were solutions. So that meant there had to be an equation where x equaled 2. There had to be one where x equaled the square root of 3. And there had to be one where x equaled 3i. Now the first one's easy. We've done that before. And that's just x minus 2. We know what that factor would have been. Here, though. Now technically, I guess you could do subtract the square root of 3, but if you've noticed, the only time we get a radical as an answer is when we take the square root of both sides. So if we're undoing this process, and we had a radical as a solution, if we're undoing it, what had to have been the original problem? Well, the original problem had to have been x squared equals something. So why don't we square both sides? We're undoing to get back the original problem. So x squared would equal 3. And we get x squared minus 3 equals 0. I really want you to compare this to this problem. My root was square root of 5, so that meant my factor was x squared minus 5. Do you see how that works? Here my root is square root of 3, and this was x squared minus 3. Now let's see what happens with 3i. Now I hope you noticed that this one had a root of 3i, so I think it's going to be very similar. If I square both sides, I would get x squared equals 3i squared. Well, 3i squared would be 3 squared, which is 9, and I squared, which is negative 1. That would have had to have originally been x squared plus 9 equals 0. You could have also noted the same exact thing here. So the original polynomial would have had to have been x minus 2, x squared minus 3, and x squared plus 9.